The paper delves into the evolution of current-carrying cosmic string networks, focusing on the Witten superconducting model. It utilizes the CVOS model to describe the statistical properties of these networks, encompassing 4 macroscopic variables: RMS velocity, energy density, charge, and 4 current amplitude. These variables are defined in terms of root mean square values of time-like and space-like currents. The research discusses the leakage of charge and current through 2 mechanisms: loop production and charge leakage, which can be described phenomenologically by introducing leakage efficiencies A and B. The time evolution contributions for Y and K are derived, indicating that the specific form of charge leakage efficiencies must be inferred from field-theoretic studies and future high-resolution numerical simulations of evolving random networks. The energy density of the noncurrent carrying network is insensitive to these losses, and the paper demonstrates how this leads to a restriction on the equation of motion for the characteristic length Lc. The Witten model introduces a critical current, which affects the network scaling behavior during the radiation era, and its implications are discussed in detail. The paper concludes with a discussion on the limitations, assumptions, and potential observational implications of the findings. The research also presents a comprehensive analysis of the evolution of current-carrying cosmic strings in the context of a cosmological network. The authors consider the interplay between the string network's characteristic length, velocity, charge, and chirality, as well as the energy loss due to loop production. They introduce an improved parametrization for the loop production function, which simplifies the system of equations describing the network's evolution. The equations of motion for the characteristic length, velocity, charge, and chirality are derived, assuming a Witten model for the cosmic string equation of state. The paper also discusses the constraints on the state parameter K, which determines whether the string is in a magnetic or electric regime, and highlights the instability that occurs when the tension becomes negative. The paper concludes by emphasizing the need for fine-tuning to achieve a dynamically stable regime, and outlines the range of the parameter that ensures a valid equation of state. The authors investigate the dynamics of current-carrying string networks, focusing on the Witten model, which incorporates a nonlinear equation of state. They derive constraints on the 4 current amplitude value, leading to a critical current limit, KCR, which depends on the chirality and string energy density. The equation of state implies a maximum chirality, KCR tilde operator O, 1, eta, where eta is a parameter related to the mass difference between the current carriers and the Higgs field. In the relevant regime, eta is defined as 1. The string network tends towards chiral conditions, with the largest deviation from chirality occurring when eta approximately equals 1. Implying 0.33 is less than or equal to KSC is less than or equal to 0.86. The authors analyze the evolution of string currents, noting that the critical current limit will have a dramatic effect on the total current, Y, which is limited by the critical current. Y is less than or equal to KCR. A nonlinear leakage coefficient, A, Y, is introduced to implement this limit phenomenologically, becoming E-dependent when Y, YCR. The authors examine the network evolution, first neglecting charge leakage and later incorporating it. In the no-leakage case, the network behavior is similar to the linear model, with the charge saturation value, Ymax, dependent on the initial chirality and scaling with the mass difference parameter, eta. When charge leakage is included, the critical current has a significant impact on network evolution, particularly for large critical currents. Eta is defined as 1. The study highlights the significance of the critical current in describing the dynamics of current-carrying string networks. The results show that the string network evolution is insensitive to the exact functional form of the charge leakage function, provided there exists a critical current above which the leakage becomes overwhelming. The impact of bias parameters A and G on the string network evolution is also investigated, finding that when they are non-negligible, the string network deviates from chirality and the evolution becomes distinct from the linear approximation. The authors conclude that the microscopic details of cosmic string networks have a significant impact on macroscopic evolution, emphasizing the need for further research, particularly high-resolution field theory network simulations to calibrate phenomenological parameters. The analysis delves into the evolution of superconducting string networks, focusing on equations of state beyond the linear case, particularly the Witten model. The study reveals that, for most physically realistic cases, the network behavior can be approximated by a linear equation of state on a macroscopic scale, rendering the CVOS model a useful quantitative tool for exploring observational constraints on superconducting cosmic string networks. Scenarios with a large current, frozen, network in the radiation era may exhibit distinct observational implications compared to simpler Nambu-Goto networks. However, the evolution of charges and currents on the network depends on their equation of state and initial conditions, making it challenging to realize such scenarios. The authors find that, when the mass of the current carrier becomes much smaller than the string-forming Higgs field, the network approaches one of two possible scaling solutions, charged or Nambu-Goto, with different scaling values, depending on the network's initial conditions. The study demonstrates the CVOS model's utility in understanding the evolution of superconducting string networks, offering a valuable tool for exploring observational constraints. The authors acknowledge the contributions of previous researchers, citing numerous studies that have shaped our understanding of these complex objects. Future work will explore the regime where the critical current has a comparable energy to the underlying strain, allowing for significant backreaction and Witten formation. The paper provides an extensive review of previous research on superconducting cosmic strains, including their formation, evolution, and observational implications, setting the stage for a forthcoming analysis on observational constraints. The CVOS model's ability to approximate network behavior with a linear equation of state on a macroscopic scale underscores its significance in this field.